Newcomb. Julie, please go ahead and share your screen. Julie is a PhD student at the University of Washington, working on program synthesis and related topics. And Julie's talk today is going to be on the synthesis of functional reactive programs.
Hi.
Thank you, Julie. Go ahead.
Yeah, quick, again, mic check. You can see my slides. We're all set up.
Yes, everything looks good. Thank you.
Excellent. All right. Hi. Well, yeah, thank you for the invitation. My name is Julie Newcomb. I'm one of Ross's students here at the University of Washington, and I am here to just quickly introduce you some ongoing work that we're doing synthesizing functional reactive programs. So functional reactive programming, or FRP, is functional programming that takes streams of asynchronous events as inputs. And some of the application domains where this is used includes Internet of Things programming, AR and VR, web programming, games, all those sorts of things. Excellent. Okay. So it won't surprise this audience to hear that writing programs over asynchronous inputs is a difficult task, and it's even more difficult for end users or people who are not professional programmers. These users can miss tricky corner cases. It's difficult for them to anticipate all the different states their program can get into over these long execution times, and these programs are difficult to debug and to test. So I have an example use case for you to think about. Let's imagine that we have an IoT controller in a smart home that operates in 3 modes. The home can kind of be in the home mode, away mode, or night mode. And we calculate this mode using the times of sunrise and sunset in our location, as well as a sensor on the front door that tracks when the occupant enters and leaves, so we know if the home is occupied or not. So now let's imagine that we have a motion sensor in the kitchen, that when this motion sensor goes off, we want the kitchen light to turn on. But when we're operating in night mode, we want it to be like kind of a soft orange light. Otherwise, we should be a bright white light. So I have here an implementation of that program in the FRP language RX, and I've drawn it as a graph so we don't have to parse too much syntax. So we have our 3 inputs to the programs. We have the kitchen motion sensor, we have the sunrise and sunset times, and we have the sensor on the front door. We have a few instances of a map operator that takes a stream and a first-class function and then returns the process stream. We have 2 operators that combine streams in different ways. We have a merge operator and the with latest from operator, which you can think of as kind of a fold in a functional programming sense. So this program has a bug. In the interest of time, I'll ask you to just believe me that it has a bug. But the point that I want to get across is that these programs really can be tricky to get right. But these programs are also very concise and expressive. You can see this program has just 5 operators for what we were trying to do. And so because these programs are so small and expressive, they're a very attractive target for synthesis. So our idea was that users often have a clear idea of the behavior of their program in kind of a normal case and kind of a happy path case, but they will miss corner cases, and they may not have even thought about exactly what they want their program to do in certain inputs that they haven't considered. So we proposed this interactive tool where the user begins with a partial specification, and the tool would synthesize multiple candidate multiple candidate programs and ask the user to disambiguate. And then we go through some iterations. The user can kind of explore the space of potential programs, and then they converge on the one that they really wanted. So what this means is that to arrive at the program that we ultimately want, we're going to have to synthesize not just one, but many programs throughout this loop. So we need a good, efficient synthesis algorithm. So it seems natural to model stream events as a list. So how easy would it be for us to synthesize functional programs that take lists as inputs? So we looked at 2 recent tools called DeepCoder and Neo that synthesize programs in a functional list manipulation DSL. I have an example program in that DSL that I grabbed from the DeepCoder paper to give you a flavor. I think it's pretty much what you'd expect to see. So we put together a tool that synthesized programs in this DSL that we built on top of the CJ synthesizer in Rosette. And we replicated their same means as randomly generating benchmarks so we can compare them with these tools. And you can see that we were able to solve slightly more benchmarks than Neo. And although our times are worse than both tools, we're kind of roughly in the same performance neighborhood. This was a pretty vanilla implementation, and we think if we'd spent some time tuning it, we could do better. But this was enough to convince us that this is a feasible approach for synthesizing list programs. So now that we believe that we can do that, we need some way to reduce functional reactive programs to functional programs over lists. So we came up with two ways of modeling event streams as list of values. And you can look at this little chart here on the left and think of it as the x-axis is time. And at the time 1, we had some event that had a value 3. And at the point 2, we had some event that had a value 2, and so on. And then I have two different ways of representing those events occurring in time. So we have what I'm calling a clock-based representation, which is kind of a sparse representation, where each element in the list represents a time step or kind of a tick of the clock. And then we have this special no event value that represents a time step at which nothing happened. And then we have an event-based reduction, where we have lists of pairs, where each pair is a time step and a value of the event that occurred at that time step. So the event-based model initially seemed more promising to us. It seemed to give us a lot more flexibility in the length of time that our event list can cover. And it makes it easier to depict the series of events where perhaps, some events occur very close together, and then there's a long interval, and then another event occurs, and so on. But the clock-based model, when we started sort of playing with synthesizing these programs, the clock-based model was so dramatically faster to synthesize that we didn't even bother running formal experiments. It just was that much more performant. So I'm going to talk to you a few reasons why that is. So first of all, this seems obvious, but the clock-based model uses half the number of integers than the event-based model, and that has an appreciable effect on solving times. The clock-based model leverages the list data structure to hold the sequence of the event, so we don't have to explicitly manage it using timestamps. And then if you think of a program that has multiple inputs, the clock-based model can walk over them in steps. Since the streams are on this clock, we know when events happen at the same time. Whereas in the event-based model, we have to do a lot of bookkeeping over our multiple inputs. So for example, if we merge two input streams, we basically have to sort those events based on their time step. And that's just more extra, algorithmic overhead that gets passed on to the solver. So you may feel that this clock-based model feels quite restrictive. We have a list of fixed size. We're kind of forcing ourselves to, take these asynchronous inputs and force them to be on a clock, which is not really what we were trying to do. The example I gave you before was a program that ran over a 24-hour cycle. But we kind of loosen our semantics a little bit and think about the clock or the time steps as just representing the point at which the next interesting thing happens to our system, and not that it's actually has anything to do that correspond with wall clock time. And if we kind of make that semantic loosening in our minds, it's actually it actually works out surprisingly well. So I will wrap up here. As I said, this is ongoing work, and I'd be happy to take any questions, but I also want to put the call out to this audience. We are actively looking for more benchmarks and more interesting problem domains. If anyone has any suggestions, I would love to hear about them, either now or offline. And I'll yield the floor. Thank you.
Thank you, Julie. Are there any questions? Oh, Radu has a question. Go ahead.
No, I don't have a question. It's just a comment.
Yeah.
So, for example, especially if you go from deterministic to non-deterministic stream processing functions, it is known that you have problems. So you don't have unique solutions. You have the Brock-Ackermann anomaly and the fair merge anomalies. And by introducing times or by introducing clock is the way to solve them. So this might be one reason why it's so much better, when you have clocks than working in an asynchronous setting. Okay.
This sounds like something I should look up then.
So it's called the Brock-Ackermann anomaly and the fair merge anomaly. But they are typically appear when you are in a relational setting, when you and it's exactly the fair merge problem. So how do you merge two streams if you don't have timing information? Now you have stamps that can say something about the time, but it's kind of, it's not explicit. So, and that's why maybe the fact you use explicit time is much better. And it turns out, look, people try to create asynchronous circuits for a long time. They never succeed. And we still have clock. So, and there is also this wall synchronization for distributed systems, which is also, this wall is exactly like you were saying, is when you put when the interesting stuff happens.
Right. Yeah. I would not be at all surprised if we are reinventing the wheel a little bit here. But yeah,
No, you're not reinventing it. That's why it works so much better. With
yeah. I think the key insight for us is that it doesn't really matter the interval between the events, but knowing when events occur at the same time was crucial.
Yeah, exactly.
So yeah, thank you.
Radu, I'll just add a quick comment that I'm not sure that is the thing behind it, because even though there is a clock, the clock is really there just to order the events the way they arrive. So I'd say it is fully asynchronous that way. And even in the case of the timestamp, you can just think of as sort of giving an ordering number to the events. And
yeah, but that's the important thing. You need to know the order. So especially when you do the fair merge, you know, if you don't know the order, then it's and this is why fair merge anomaly happens. If you have several strings and you have no information about their relative ordering, you don't know how to do the merge, you know. And that's
something to look into. Thank you.
All right. With that, I think we can bring the session to a close. Thank you all, and thanks to the audience for staying with us for an extra 25 minutes. And we'll see you all next week. Just a sneak peek is next week we'll go back to a tutorial, and this one will be a tutorial on machine learning because we're seeing more and more use of machine learning in synthesis. And so we hope you'll all find that useful. All right. Thank you.